for inviting me. It is a great pleasure to give a talk at Lando's conference. And it seems to me, I know Sergei Lando for several hundred years, and you can see at least for the last 100 years, he didn't change, not a bit. Okay, so I will speak about symmetric chromatic function in Starbases, and basically it is kind of, I'd like to report the result of my student, Ishaan Shah, former student. Right now he is a graduate student in Rutgers, who discovered some elegant formula for the chromatic symmetric function. So that is the plan of my talk. So I will speak about Stanley's chromatic symmetric function and our approach, very old approach, which we did in the jointly with Sergei and also Sergei Duzhin to the chromatic symmetric function. And then I will start about expression of this chromatic symmetric function in different bases. And in particular, my goal is that item 4 and chromatic symmetric function in Starbases. But probably I will say a little bit about the other bases as well. Okay, so let's start. So the Stanley introduced the chromatic symmetric function of a graph in 1995, and that was the definition. So it was a sum over all colorings of vertices by natural numbers. And there are also infinitely many variables here corresponding to the natural numbers. And the terms are summing is going to be the product over the vertices of the graph of the x with a subscript, the color of a vertex. Altogether, this is going to be a monomial of degree, the number of vertices. So the product of x's and the number of those x's will be the same as the number of vertices on the graph. And I'm summing up over all such maps, such colorings, which are going to be proper. And proper means that it should be like the different vertices are colored by different colors. Okay, so that is
you mean
yes.
adjacent vertices.
Adjacent vertices are colored by different colors, right? The vertices which connected by an edge. So it's supposed to be different natural number attached to them. And that is a formal power series. Yes. Yes? Some question? All right. Okay. So let's do probably some examples. And it is a symmetric function. If I make a permutation of those x's, then the function stays the same. Of course, it doesn't matter which particular number I color the vertex. What is important is that the adjacent vertex is colored by different colors. And as a symmetric function, I can express it in various bases. Elementary symmetric function, the most kind of famous. But also there is I will work with the power function basis. So I introduce that symmetric function P subscript M as a sum of the m's power of all my variables from 1 to infinity. And in terms of that power function basis, let's consider the example, the simplest example, when the graph consists of two vertices connected by an edge. Then I can color one vertex, say by 1, and the second vertex I need to color by 1 is forbidden, so that is what its hat means. So I have to drop this term, but I can color the second vertex by 2, 3, and so on. but not 1. So that is, that means here I omit this term. Okay. Then I can color that first vertex by 2, and then the 1 for the second one will be allowed now, but what will be forbidden is 2 for the second one, and so on. So I have that line corresponding to the coloring by 2. And then it will be by 3, and so on. And what will be at the end? At the end, I will consider, I will sum up all these terms, including those which I suppose to drop. I will subtract them after all. And when I sum up, I can factor out x1 from the first row, x2 from the second row, from the third row, and what will be inside of parentheses here, it will be the sum of all x's in each row. So I have like p sub 1 that is the sum of all x's, and it will be squared here if I sum up all of them. So that is going to be, probably I need to take it smaller, or maybe even like that. Okay. No, that is not good. Wait a second, I go too far. Yes. So when I sum up them all, it is going to be p sub 1 squared. But now what I have to remove is those terms with heads. That is going to be x1 squared, x2 squared, x3 squared, and so on. That is p sub 2. So that is the expression. That is a symmetric chromatic function for such a graph. And the usual usual chromatic polynomial will be obtained if I plug in, make all these variables p's are equal. So I make it lambda, then it will be lambda squared minus lambda, and that is the number of colorings of this graph in lambda colors. So the classical chromatic polynomial of the graph. So it is a generalization of chromatic polynomial. But in general, there is that formula for symmetric chromatic polynomial like that. So it is a sum goes over all subsets of ages. And for the given subset, I have the sign -1 to the cardinality of that subset. And then I have this product of p's, various p's, which corresponds actually to the partition of the number of vertices of the graph. And partition corresponds like that, works like that. I should take the spanning subgraph with s ages. For given s, I take the spanning subgraph which contains only ages from s. And then for such spanning subgraph, I consider connected components of that. And lambda 1, lambda 2 will be the number of vertices in connected components of the spanning subgraph. And I will take the product of all these power functions corresponding. Again, there will be k connected components, and that is going to be the product. And if I use this p sub lambda for partitions, the standard notation in combinatorics, so I have that formula for the symmetric chromatic function. And now let's look for the examples here. So again, let's start with this example. There is only one age, so the possibilities for the subset of ages, it is either the empty set and or the whole set. If it is empty set, then there are two connected components there, and each of them has one vertex, so that is corresponds to this term p1 squared. And if I take the whole age, so all the only age here, then I will get only single connected component, so it will be only one p in that product, and there are two vertices, so p sub 2. That is what we have here. Now for this graph, I have like two ages here, and I can take no ages, so empty subset. then it will be 3 connected components, P1 cube. I can take one edge, then it will be 2 connected components. One of them is 1 vertex and another 2 vertices. So P1, P2, and there are 2 possibilities, this edge or that edge I will take. And if I take all 2 edges for that subset, then it is going to be P sub 3. So that is the example here. And let's look for more examples. So for triangle, it is going to be like that. Again, it is very easy to figure out for the small graphs with that formula what it will be when there are not so many edges. But in general, yes, what is interesting here that in general, if again I consider it as a symmetric function, so plug in that power function there, then for the complete graph, for example, triangle K3, it is going to be essentially elementary symmetric functions and elementary symmetric function for Kn. So if I plug in the sum of cubes here and all this sum of x's and cube z and so on, I will get elementary symmetric function as a coloring, and that is the like coloring 1 color, so that has to be different 2, that has to be different 3, and that is all elementary symmetric functions, only n factorial because I have that automorphism group of n factorial. So that's how this thing works. So elementary symmetric function is chromatic symmetric polynomial of a complete graph, essentially, up to that factor, numerical factor. Now, if I have like a path of length 3 or 4, doesn't matter how you count. So you have this one, and that is another example of symmetric chromatic polynomial, which is again not difficult to figure out. And finally, I have that graph, and the chromatic, it has to be subscript 5 with symmetric chromatic polynomial like that. Okay, and since then, since Stanley introduced it in 1995, there are a couple of open conjectures. One of them that this symmetric chromatic polynomial distinguish trees. So the usual classical chromatic polynomials, all trees are equal for the same number of vertices. That is the same chromatic polynomial, but symmetric chromatic polynomial distinguished all trees. And then there is another one which is related. So for some special graphs, which are called incomparability graphs of some partial ordered sets, the graph, the symmetric chromatic polynomial of such graph is has positive coefficients if we express it in elementary symmetric functions in that basis. All right. So now I will go to our old work, which actually was earlier than Stanley's, published 1 year before Stanley's, and it was related to the Vassiliev invariance. We are motivated to the Vassiliev invariance, and we essentially introduce that polynomial, that expression in terms of p's, in terms of the power bases. So the weighted graph, we come to the weighted graph, studying the combinatorics of Vassiliev invariance. We come to that notion of weighted graphs. That is the graph without loops at multiple edges with the weights on the vertices. So it is not a coloring, it is the weights which stands there. So every vertex is weighted. It looks like the same as coloring of vertices, but I treat it differently, that function. So the natural weight for every vertex. And if I have just a graph, usual graph without vertices, I can think about it as a weighted graph where weights of every vertex is equal to 1. So then we consider the vector space spanned by all weighted graphs of the total weights. When I sum up the weight over all vertices and total weight n, and we make a quotient of this space by that weighted contraction deletion. And the weighted contraction deletion, we delete an h, or we contract an h, and we sum up it was a vector space spanned by that, so linear combination of such graphs. So we can sum of this and make a quotient to that. Only for the contraction, it has to be careful. The contraction, I contract an h, but it's the weights supposed to be sum up. So that is the main property. And also, if there are, after contraction of a weight, if there are multiple ages occur there, I have to reduce them to a single age. So no multiple ages would be there. So I reduce them to a single age. So that is the relation. And if I take, again, vector space spanned by all weighted graphs with the total weight n, and that is the homogeneous of degree n, the total weight of all of these graphs will be also n. So I can take a quotient space, and that is going to be this one. And finally, I will take the direct sum over all n like that. And it happens to be that this is going to be a Hopf algebra. There is a Hopf algebra structure. The multiplication, it is just joint union of graphs, again, induced on that quotient space. And co-multiplication, when we have a graph, we split the vertices into the two sets and take the induced subgraph on one set and another one, and then the product of that. That is the co-multiplication, and there is an antipode there. So it is a Hopf algebra, and that as a Hopf algebra, it is very simple. So it is commutative and co-commutative. And any such algebra turns out to be the algebra of polynomials over primitive space. And the primitive space in this one, so that basically was the main result of this paper, that the primitive space of this Hopf algebra at each degree n has the dimension 1. And it will be spanned by a single vertex, the graph which consists of single vertex, but the weight of that vertex is n. And so that is the classical theorem that each such commutative and co-commutative Hopf algebra is isomorphic to the polynomial algebra at the variables, and that variables corresponds to the basis of the primitive space. And again, for each weight, it will be only one primitive space for such graph. And now, if I take the graph and I consider it as an element of this Hopf algebra, so that means modulo this contraction deletion relation, I will get an element of this Hopf algebra H, and as such, it will be can be represented as a polynomial in variables corresponding to the basis in primitive space. But for basis in primitive space, I need just one element at each degree. And so it will be a polynomial there. And again, if I take the primitive space, basis in primitive space consisting of a single vertex of weight n, then it is going to be Zx would be Q, the variables Q. And later on, Nobel and Welch actually observed, noted that if you take our weighted polynomial and instead of variable Q, I plug in negative P, P sub J instead of each of them. So basically make a little change of variables and multiply it by the sign of whole polynomials, that what we will get this exactly Stanley's symmetric chromatic function. So basically the expression in terms of P's are the same as expression as our polynomials, weighted polynomials, only with a a very small change of variables, and that change of variables was because actually for p's we could get this one as well, but what we will need instead of sum up here, we will need to get minus as for chromatic polynomial, minus in that contraction deletion relation. Then it is going to be, we will get exactly the Stanley's symmetric chromatic polynomial. But anyway, this is a kind of a very minor substitution. So basically it is the same thing as Stanley chromatic symmetric polynomial. The only thing when we were thinking about this in the context of Vassiliev invariance, we didn't plug in any, we didn't think about it as a symmetric function. We didn't plug in any power symmetric function instead of our variables q. So we were happy with this polynomial and didn't do anything further. So we didn't contribute to the theory of symmetric functions, but it was there. Okay, and let's go over a few examples. So again, I can delete this h or contract it. When I contract, I will get a vertex of weight 2. So it is going to be q1 squared. That is the product. Product is joint union, and that is q1 of weight 1. There is no weight here, so weight 1, q1 squared plus q sub 2. And again, if you do this substitution and multiply it by -1 squared, which is 1, because there are 2 vertices, you will get exactly the previous examples of the symmetric chromatic polynomial. So it is as easy as that. And here I can delete or contract also of those things. I can delete that or contract it, that will be this one. Then for remaining graph, I can delete this, it will be that one, or contract it. When I contract it, I will get one vertex of degree 1 and one vertex of degree 2. And the same graph comes from here, so that will be coefficient 2 there. And then a degree 3, a weight 3, if I contract these two. So that is the polynomial for this graph, weighted polynomial, and so on. Okay, then I would like to speak about expression of this symmetric chromatic polynomial or weighted polynomial, doesn't matter, in terms of the different bases for the symmetric function. And it comes formally in that paper about chromatic basis for symmetric functions. And the theorem is that if we, for every natural number, if we choose fix a graph with n vertices, connected graph with n vertices, then the symmetric family of symmetric chromatic polynomials form a basis for the algebra of symmetric functions. So algebraic basis. So it is like elementary symmetric functions or power functions. So the basis in terms of linear algebra, in terms of span, it is going to be monomials in that one. So this function, symmetric chromatic polynomials of such graphs, will form a basis for that algebra. Algebra as the basis of algebra. So every symmetric function will be a combination of the products of such symmetric chromatic functions of those graphs for any basis. And when I saw this paper for the first time, I just realized that we knew actually the proof of this theorem in 1994 when we were working about this, because from our approach from the Hopf algebra, it is a sort of absolutely trivial, and that is going to be, that is our paper when we were working about this. The point is that if I consider this, so that is the proof, and that is the end of the proof. So just 2 lines, and if it will be the smaller font, it will be just 1 line. So if I consider this graph as an element of the Hopf algebra, then because of the symmetric, because of the deletion contraction relation, so the projection of this graph on the primitive space will be non-zero. So I just contract these edges, and of course at the end I will contract everything, and sorry, that will be the one vertex of weight n with a certain coefficient when I will contract everything there. So, and that coefficient will be non-zero. So its projection to the one-dimensional primitive space is non-zero. So that means that I can choose that element as an element of the Hopf algebra as a, well, its projection as a basis on the primitive space. So that means that this as an algebra will be generated by those elements, by those graphs. And that's it. However, as I said, we didn't think about symmetric functions. And so we didn't formulate this theorem, but it was a sort of obvious for us at that time. And it is a nice theorem because it gives a kind of an interesting and funny basis, other basis of symmetric, of the algebra of symmetric functions. Moreover, we can choose not only just a graph with the n vertices, but we can choose a weighted graph with a total weight n. So this is G sub n tilde, and then the weighted chromatic polynomial of that. If I make a plug in this power function there, then it is going to be the basis for all algebra of symmetric functions. And in particular, if I choose one vertex of weight n for each one, so that corresponds to our variables q in our weighted symmetric function. So that is going to be a basis, and that basis is the power function, power symmetric functions in the symmetric function. Now, if I choose as that family of graphs, if I choose the complete graphs, so complete graph with n vertices, then, as I said, that symmetric chromatic polynomial up to a constant, it is elementary symmetric functions, and that gives me the basis of elementary symmetric functions for the algebra of all symmetric functions. And now I would like to work to speak about Starbases. So the graph, star graph, that will be the graph like that. So this is G with a subscript n, the graph with n vertices. And if I want to speak about weighted graph, that will be all weight 1 in the Hopf algebra element. And if I take this symmetric chromatic function of such a graph, that is the basis in all for all symmetric functions. And it can be expressed in terms of power symmetric functions according to that formula. So it is very easy because it is very symmetric graph. And I have to take a subset of edges of say of k edges here, and there is an n-1 edges in general for G sub n. So I can choose n-1, choose k, and those edges has to be contracted. So that gives me p k plus 1 because there are k plus 1 vertices will be in that star. But the rest of them deleted, and I will have isolated vertices, and that corresponds to this p sub 1 to that power. So that is the expression of this symmetric functions in terms of that one, and in particular, if k equals n-1, the top term, that is going to be k equals n-1, so that will be p sub n. So it starts with p sub n there, and some smaller term product with non-zero powers of p sub 1. So that gives another proof, or that particular proof, that this is the basis of symmetric functions. So p sub n, it is s sub n up to the product, up to the decomposable elements of the smaller degrees. So it is like an upper triangle matrices for the change of basis there. Okay, and now that is the formula for the symmetric chromatic function in terms of the star basis. Again, I have this S, S1, S2, and so on, Sk, as the symmetric chromatic function of the star graph. And the formula says that it is going to be, if I express it in terms of Z basis, it is going to be the sum over 3 partition of the set of ages. So I represent the ages as 3 non-union of the 3 disjoint non-intersecting parts, E sub 1, E sub 2, E sub 3. And for E sub 1, it's supposed to be even more, less than that. It contains all leave ages. So the ages which end up with a point connected of degree 1 connected to nationals. So that is going to be in one part, and there are 2 other parts. And now I have that negative S1, that is the variable which corresponds to a single point, the star with 1 vertex. And that one will be raised to the power number of elements in that second part in that 3 partition of the set of ages. And then I multiplied by S corresponding to a partition, some lambda partition. So it is going to be a partition of the number of those ages E sub 1, only I will put this quotation mark for partition because actually the zeros are allowed here. So it might be the zeros as well. And it is defined like that. So first I consider that union E sub 1 and E2. E1 and E2, and take the spinning subgraph corresponding to that union E1 and E2. That spinning subgraph, it will be in general disconnected, and and I take like a connected component of this spinning subgraph. And then the case element of that partition, lambda sub k, is going to be the number of E1 ages. So there is the spinning subgraph in the union E1 and E2, but it will be E1 ages in that connected component. And then that S variables, the product, it will be the first connected component, but I add 1 because that number of vertices will be 1 more in the star. So basically, E1, that will be the ages which form the star, but the number of vertices will be 1 more. 1 more here, 1 more for the last part, lambda sub L. That is the number of, again, E1 ages in that connected components, L connected components of the spinning subgraph with such thing. And so that is why lambda is allowed to be 0. Sometimes I have no ages. I have like isolated vertices in there, so there is no ages, E1 ages in that at all. So that will be 0, but it will be the variable S1, the same variable corresponding to isolated vertex as the star of 1 vertex. And let me do an example, and just I label by colors the ages here, just to figure out to sort them out, what it will be. And that is the Dinkin diagram of D5. And nevertheless, that is the graph for which I would like to figure out that to apply this formula, the star basis. So E1 supposed to contain the blue age, the green one, and the yellow. So those are the leave ages. That is the E1. But there are 2 choices. Also, it contains the red one, so it will be everything there. Or it does not contain the red one, only just the leave ages here. So in the first case, when there are only leave ages, blue, green, and yellow, then there are 2 choices for E sub 2. It has to be E sub 2 and E sub 3 form the entire basis. One of them is E sub 2 is an empty set. And that means that E sub 3 is going to be the R. Okay, empty set. So that means E1 union E2 is going to be just the leaf edges B, G, and Y. And there are two connected components in the spanning graph. That is going to be one connected component, that is another one. And I need to take the number of edges there. There is one edge and there are two vertices, so that is S sub 2. That is in this connected component, it will be two edges, so three vertices. That is the star of S3. Three vertices here. So I will take that product. That is the contribution into there. Now, the second possibility is the same E1, only the leaf edges, but E2 is going to be consist of this R. So E3 is 0. Then the spanning graph with the union E1 and E2, that is the entire graph here. And for that graph, there is only one connected component. And I need to count the number of E1 edges in that connected component, which is just 3. So 1, 2, 3. So it is going to be, then it is going to be S4 corresponding to these connected components. But in that case, E2 consists of one edge. So it will be negative S1 as that factor in this formula. So negative S1, S4 will be the contribution to this graph from that choice. The last choice where E1 contains everything, there is no room for the other two sets. So it is going to be the empty sets then, and all edges are E1 edges, and there are 4 of them. So it will be just S4 plus 1, S5 will be that one. And basically that's the result. So that's the answer. And my students actually come to this, they were a sort of very excited about this Stanley's tree conjecture. It is indeed very attractive conjecture that the chromatic symmetric polynomial distinguish trees. But so they wanted to work on this tree conjecture, Stanley's tree conjecture, so which of course very difficult, regardless that it is a simply formulated. But the difficulties with tree conjecture is that symmetric chromatic polynomial contains actually a lot of redundant information. And the difficulty is to get rid of redundant information, to get a more concise, more dense formula for this one, which contains just a necessary information about the trees, not redundant information. And so that is the one way what they did, they come to that Starbases and looking for this expression in terms of the Starbases. So that was their motivation for this research. And if we compare it with what it was in the power basis, you can see that it is going to be like that. So that is what I mean. There are a lot of redundant information. So there's a lot of terms here comparably to just 3 terms in the Starbases. However, again, for the larger graph, of course, that is going to be also a very large polynomial. So it does not get the solution of this tree conjecture at the end, but still a nice formula over 3 partitions. Okay, and I am going to go over a proof of it because the proof contains also an interesting ideas. So the idea of that Ishaan Shah, that student, was not to contract the edge, but to replace it by a sort of squiggle, and that squiggle will indicate that we will contract it at the end. But just keep it as it is, just to use this squiggle edges to mark that these edges are subject to be contracted at the end. And so we have this contract. Yes.
Sergei, what is the Russian translation for the word squiggle? So as to be.
Good question. Не знаю. Волна.
Okay.
волнистое ребро.
Okay.
Is it okay? All right. Okay, all right. So we have squiggles instead of just immediate contraction. But again, we will think about it at contraction at the end, and only that squiggle also gives this information that it will be the vertex of weight 2, because that is the number of vertices to be contracted together. So that's that squiggle. So that is the contraction deletion relation. And then since that squiggles, so at the end it will be a lot of squiggles there, they are going to be contracted. That means that all connected graph with squiggle edges are going to be the same. We have to contract it to a single point of that weight. In particular, that graph here, this one, all trees are the same. Also, we can make cycles like that. Like this one, complete graph, they are all the same with squiggles, because again, squiggles are going to be contracted. So I do not basically care about this one, but I will keep them squiggle. Okay, and then basically that is then there are two stages in the process. So I'm going to apply this process once. That contraction deletion relation to all edges on my graph. And that means that some of them will be deleted. I will choose this one, and those which are deleted, that is the part E3 in that tree partition of the graph. And those which are going to be squiggle, that is going to be the union of E1 and E2. So the complementary set of edges to E3, to those which are deleted or not deleted, the squiggle, that is E1 union with E2. All right. Now each term will be the graph with squiggle, only squiggles there. And it will be several connected components in general, but in each connected component, I can rearrange the squiggle in the way what I want to the anything, and I will rearrange the squiggle into stars. So if the graph is connected, I will just remove all the cycles and do just the stars from the squiggle. And again, the total number of edges is going to be E1 union with E2. That is the one. But for each connected component, I can consider it as a star of squiggles. And then I am going to do it backwards, the same contraction deletion. I am going to replace the squiggle until now it is only stars of squiggles. Squiggles to either empty edge or the straight edge, the usual edge. So that is the same contraction deletion, only I just move these terms around like that. And once I will do this, then for each those edges which are going to be those squiggles from stars, which are going to delete, that will form E2. And those which I'm going to replace by a straight edge, for which I choose that thing, is going to be the set of E1. And now yes, so for those for which E2, when we delete it, then it appears with a sign. And first, when it was a squiggle, it was the sign for this term. Probably it has to be somewhere on the previous pages, right? The sign of the term with the squiggle is going to be -1 raised to the number of squiggles, because each squiggle is with minus. And again, it minus for symmetric chromatic. If we would do like weighted polynomial, like in our approach, it will be all pluses, and I can forget about minuses. But the number of squiggles, and the number of squiggles will be E1 plus cardinality of E1 plus cardinality of E2. Okay, and now I replace squiggles to the straight edges, and that is going to be right? And that is going to be E1. That is the straight edges is E1. So the total sign is going to be -1 to the cardinality of E2, the set of E2. That was the original formula, that cardinality. And also, when I delete that edge, the squiggle forms a star now, the star of squiggles. When I delete, then it will get isolated vertex, and that corresponds to S1. So also it will come to S1 when I delete this edge. And so that will be the total result. And so that will come to the total thing. The only there are some cancellation in this process. The cancellation comes that from the fact that if I take E1, which does not contain the leaf edge, that means that that leaf edge, it goes either to E2 or to E3, which is E3 deleted from the very beginning, and E2 deleted on that second stage when I replace squiggles to this one. And these two choices lead to the same stars. The only thing they differs by a sign. So if it is in E3, then it is E3 stands there. But if it is in E2, so that means on the first stage it was replaced by squiggle, so it has extra minus here, and then it is deleted. So this thing will cancel out, and we will come to that E1 must contain the all leaf edges. Otherwise, it is just, we come to that formula right here. Otherwise, it is other choices for E1 which do not contain, when there are the leaf edges outside of E1, they will be canceled out in that formula. The formula will be true, but it will be more terms. So it is basically more economic way to say this, this formula. Okay, now let's see. So, and that is the end of the proof. And the same procedure actually can work in the different bases of the symmetric functions. For example, I can take the path bases. So I will call them A's. So A sub 1 will be just one vertex, and that is the same as S sub 1, P sub 1, everything. But A sub 2, it is symmetric chromatic function of this, A sub 3 is that one, A sub 4, and so on. So I can choose that basis in symmetric functions. And then it is going to be the similar formula, only in that basis, I do not have that cancellation. So it have to be tripartition of the edges. Also, it is -1 to the E2. And that is the product of A variables, and it defined like that. So again, I take E1 and E2, the spanning subgraph containing these edges, and take the connected components of that. Then from each connected component, I construct a path with those edges, E1 union E2. The edges will be in correspondence to E1 and E2. And then I remove that E2 edges from a path now and take all choices for E2 from that set. And then if I remove some edges from a path, that is going to be a union of paths, and that is the product of A variables after that. And so it is going to be the similar formula, and that is the result. And for example, for A5, and you can observe that this in the path basis, actually the answer is exactly the same, almost exactly the same as in the star basis. The difference is that these two terms comes with the opposite sign. I don't know why. That was like a calculation. I calculated that example, and it happens to be like this. I do not know whether it is just a coincidence or something more deeper hidden here, why actually they are related like this one. And again, that old calculation in terms of the power basis, it contains too many terms and too much extra information, which we do not really need to that. Okay, and that is the end of my talk. So happy birthday.
Thanks, Serежа. Thanks for a very nice and clear talk. May I ask a couple of questions?
Sure.
These two guys who proved that any sequence of connected graphs with increasing number of vertices provides a basis for the space of symmetric functions. How did they prove it? Was it difficult or?
Good question. But I have to confess that I didn't read this paper. This paper were found by my students. So they found my students and they said, oh, you know, there is such a remarkable theorem. They start to explain it. And I said, this theorem is trivial. And I just realized that we knew this in 1994 and I just didn't look at this paper. I'm sorry. But I expect it should be something like that. Anyway, well, what other, maybe not. Maybe they did it more down to earth, not using the Hopf algebra, but just realizing that the power function or elementary symmetric function is like change of basis will be a kind of upper triangular. So in those formulas, you have this top coefficients at P sub n to be non-zero, and that was the proof. What else? So direct proof. But again, I didn't read this paper.
Okay, and what are the difficulties which people meet and you meet in particular when proving Stanley's conjecture on distinguishability of trees?
Well, we didn't prove it. We didn't succeed. We tried.
Yeah, but you tried.
Difficulty is exactly to nail what sort of information is necessary for the two trees to be different. So, and there are a lot of again redundant information like P1 raised to the power n. It appears in all of these polynomials. So that is a sort of trivial. This is the number of vertices. Then there is a top term. It is always going to be P sub n in power basis, or S sub n, or whatever, A sub n. So, and there are a lot of relations between those coefficients. You can interpret that the first coefficient, the last coefficient, but it is very, very easy. So basically, what you are saying from those coefficients that the trees with the different number of vertices are different, but that is not enough. But what is a kind of characteristic information which would characterize the trees up to isomorphism? Which trees are isomorphic, which trees are not isomorphic? That is difficult. And that conjecture was checked, by the way, on computer up to I don't know. I saw several years ago, I saw 22 vertices, but my student told me that it is 29 already vertices. So quite far from the, it was checked. So it is believable that it is true. But again, the difficulty is just to get that information which would distinguish your trees.
Okay.
Did I answer?
Yeah, I see. Right. Maybe other participants have questions. Спасибо еще раз.
Очень приятно. All right. Okay.
Maybe I can ask the follow-up questions on these trees. So as far as I understand, every tree gives you a function on partitions of the number of vertices.
Yes.
And you want to prove that if the functions are different, the trees are different.
Right. Yes, exactly. Yes.
And okay, and so when I see a function on partitions of n, usually it corresponds to a central element of the symmetric group that acts by a constant in every representation. every time I met functions like that, it was always in the same context. So I wonder if there is some remarkable element in the center of the symmetric group that you can assign to a tree.
Interesting question. I have no idea. I didn't recognize it in that way, but it is an excellent observation. I cannot just say anything about this, but thank you. It was a nice observation. Yeah. I don't know.
Yeah, okay.
I don't know. Okay. Thank you.
Right. So it's a good point to switch speaker to Dima.
Okay.
Yeah.
Yeah.
Yes. Right. Okay.